Well, hello to Joey and Eric. I tried to record my lecture during class this afternoon and something went wrong with it, so I'm going to try and go through things as quickly as I can so that you have those notes from Chapter 2. Chapter 2 does have a number of terms, and again, what you're going to have to do with terms primarily is to simply do some matching of definitions with them. A frequency is just how many of the data there are in a certain category or range. You just count up how many there are. So like the frequency of students in period 4 statistics is 2. If I did the frequency in period 7 statistics, that would be 7. You just count up how many there are. There are some variables we use for frequency. N is the total number in the sample. X is how many are in a certain category. So like maybe N would be all of the students taking stats, which is 9 this semester. X would be the number of you guys in period 4. That would be 2. Another term that comes up is relative frequency. The only difference between frequency and relative frequency is relative frequency, we're talking about a percent instead of a raw number, or a fraction instead of a raw number. So for instance, since I have 9 students altogether and 2 of them are in 4th period, then I could say 22% of my class is in 4th period. That's the relative frequency. A frequency distribution is basically just a chart that shows you how many are in different categories. So we'll look really quickly at a couple of examples of frequency distributions. Here they've got some numbers, they counted up how many times each of them happened, and I can see, gee, 2 was the most common score. Same kind of thing on this one. You can look at it and figure out lots of people had 1 pet. And again, here's some other frequency distributions. You're just counting up how many things are in each of the possible categories. Sometimes those categories will be ranges of numbers. Here we might be looking at maybe a question that was asking people how old they were. And I could say there were 12 people that were between ages 30 and 35, and 6 people that were between ages 6 and 11. Here, again, it's just a range rather than a specific number I'm looking at each time. Another term that goes along with that is the word histogram. All a histogram is just a bar graph that shows you a frequency distribution. So like here, we're looking at how old people that said M&Ms was their favorite candy were, and we can see that the most common group that said that was your age. This is just showing you a bunch more of histograms. Again, it just ends up being a bar graph that's showing the number in each category. Something your book makes a big deal of is different kinds of distributions. And in the printed notes that I'm going to give you, you might want to make a big star or highlight by these because it's actually one of the more important things we're going to talk about. There are a bunch of different kinds of distributions, but there are 4 of them that really end up being more important than the others. The first of which is what's called a uniform distribution. The idea of a uniform distribution is that each of the categories or ranges has about the same number in it. It doesn't have to be exactly the same, but it's pretty close. An example of a uniform or a rectangular distribution would be if I counted up how many students there were in each of the classes at Garrigan. It's not exactly the same, but it's pretty close all the way from elementary school up to high school. So that's pretty close to uniform. Here's a line graph that's showing a uniform distribution. And here's a bar graph that's showing a uniform distribution. Again, it doesn't have to be exactly the same in each category, but it should be close. A couple of examples of things that could be uniform distributions. I actually had someone who for their project once rolled a die over and over again and just counted up how many times it landed on each number. You'd expect it should be pretty close to 1/6 of the time for each of the numbers. And in fact, that is what he got, was close, but not exactly that number. Another thing that would be pretty close to uniform is the day of the week that babies are born on. Now, I will tell you in the real world, there actually are fewer babies born on weekends and more born on weekdays. That's because the doctor doesn't want to come in and work on Saturday and Sunday. So a lot of times they'll like induce labor in a mother on Friday to avoid that problem. However, especially if you went Monday through Friday, the distribution is pretty close to the same. Next up among the distributions is a skewed distribution, which is just top heavy or bottom heavy. There's more data on one side than the other. Again, I've got some graphs that show you what the distribution might look like. You can see this one is much bigger at the left than toward the right. Here's the same sort of thing shown as a bar graph. We often talk about skewed distributions having a hump and a tail, and this one tails off to the right, which is why we sometimes will say this is skewed right. A couple of things with skewed distributions. One of them is grades in a class. I put a college class, but it honestly would be any class. When I give a test, I hope the grades are skewed because I sure hope that there's a lot more A's and B's than there are D's and F's, that it's, heavy on one side and very light on the other. Another thing that would be skewed is the incomes of people that own stocks. Typically, wealthier people are much more likely to own stocks than poorer people, so those incomes would be skewed. The third one, and it's by far the most important of the types of distributions, is a normal distribution. Here's where you really might want to put a big star down on your notes. Normal distribution, it's big in the middle and small at the sides. It has a hump just like a skewed distribution, but this time it's going to tail off both ways. And it ends up coming close to making a mirror image. We sometimes call that a symmetrical distribution because it is close to being the same on both sides. And especially in places like psychology, they'll talk about a bell curve. Hopefully, if you look at that picture, you can kind of see where that name bell comes from. Again, you can see the same sort of thing with a bar graph. This is actually a mathematical graph of what is the official bell curve or normal distribution. And I will say the axes actually are stretched a bit to make it look a little bit more like a bell than it normally would. But again, you can see it's big in the middle, it tails off on both sides. And I came across a picture that talks about a paranormal distribution that I thought was kind of funny as well. The reason normal distributions are important is that they are typically considered the best kind of distribution when we're working with statistics. And in fact, anytime you have a large population, almost any characteristic will end up taking on a normal distribution. You could think about something like how tall people are. You got some people that are midgets, and you got some people that are really, really tall, but the vast majority of people are in the middle. They're normal, which is literally where that term comes from. The last kind of distribution is what's called a bimodal distribution, which literally means there are two modes. You've got two most common values or two humps in your data. Here's a picture where you can see there's a cluster at the left and another cluster at the right. That's bimodal. And again, the same sort of thing happens when you have a bar graph. Bimodal data actually happens all the time when you have statistics that can take on different values for men and women. For instance, you could look at sports records over the years, and very often you will have different records for men than you do for women just because of the nature of people's bodies, and it will form a bimodal distribution. There's some other terms that we sometimes use when we're talking about data as well, a couple of which I actually talked to you guys in class about yesterday. A cluster is just a place where there's a lot of data, where things group together. And if you happen to see a cluster, that's kind of where you want to focus in on when you're looking at data, because if there's a lot of stuff there, you should probably pay attention to it. A gap is just a place where there's not much data or sometimes very little data. It's like you have a bunch of stuff, and then there's nothing, and then there's something else. The nothing is the gap. If you go beyond a gap, you often will find an outlier, which is just something that's much bigger or much smaller than everything else. It lies outside. That's why it's an outlier. I used the example before of maybe you have somebody that had a score on a test that was much better than everybody else that took the test. That would be an outlier. In the picture you're looking at here, there's somebody that did way worse than everybody else, and that makes them an outlier. Again, an outlier is just something that lies outside of the main stuff. It's different from the trend. When you're looking at data, you do want to recognize gaps and outliers, and basically ask yourself why. I put in here a picture of Wayne Gretzky, who, like 15, 20 years after he retired, still holds a whole bunch of hockey records. And he would be an outlier in many ways. You can actually see his dot clear up at the top right of the graph. And yeah, that's because he had more goals and assists than pretty much anybody else that's ever played hockey, so he lies outside of the trend. We already talked about most of the ways of organizing data, but I'm just going to add a couple of things to what I talked with you guys about personally. Again, the first main way is a bar graph. What a bar graph does is it just shows how many are in different categories. Your book talks about a special type of bar graph, which is what's called a Pareto chart. All a Pareto chart does is it just sorts out the bars so that they go from biggest to smallest. We do that just because in English we read from left to right, and so you can quickly look at something and recognize what we need to focus in on. Like in the customer service one at the bottom, I can say, well, maybe we need to look at lack of training and inadequate pay. That's where our focus should be. Like any bar graph, you can either go vertically or horizontally, but again, a Pareto chart, you put the big one first and the small one last. Something else that essentially is a bar graph is what we call a pictogram or pictograph. All that does is it uses little pictures to literally make the bars for your bar graph. Now, the example I'm showing you here is actually not a good pictogram because they don't have any label that tells you like how many days each of the symbols is standing for. However, I can look at that and just right off tell you it was sunny way more often than it was cloudy. Here's a couple of other pictograms, and like it says, you do want to make sure that, well, it can be a cute way of communicating information. You got to make sure that you do still communicate clearly. Second of the big three types of graphs is a circle graph, and again, the key thing with a circle graph is it shows percentages, and those have to be percents that make a whole, that add up to 100. You sometimes will see circle graphs that have raw numbers in them, but they always have to combine to make the whole. So like in this picture, I can tell that people only had 4 kinds of pizza they could choose from because these percents do add up to 100%. So, nobody chose anything other than the 4 that you see there. And I kind of got a laugh out of this circle graph or pie chart because you sure can't argue with the pie I've eaten and the pie I've not eaten. There are some variations on that kind of show the same thing. Like sometimes we'll talk about a donut, which is literally just a circle with a hole in it, but it works exactly the same way as a circle graph. Another way we can show percentages is using what we call a divided rectangle or a thermometer graph, which basically just divides up a rectangle instead of a circle. You might remember when they were doing the fundraiser to raise money for the chapel, there was a big thermometer graph that was in the lobby of the school where they showed what part of the goal for paying for the chapel we had met. And a lot of times that's a use that people will use those for. Here's another divided rectangle where they're showing you the part of the cost of an airplane ticket that goes to different purposes. And this is probably something the airline published to show that their profit is almost none of it. Third key kind of graph is, of course, a line graph. Your book calls that a time plot or a time series graph, and that's not a bad term because, as I mentioned to you guys before, the big point of a line graph is it should show how things change over time. Like here's a graph that obviously it's well in the past, but you can see that in 2001 there were definitely more dolphins in Santa Barbara Channel than there were in 1996. It went up and down over time, but it's definitely more at the end than at the beginning. A special kind of line graph is what we call an ogive. I've actually heard that pronounced both ogive and ogive. This shows what we call cumulative frequency distribution, which just means what you've got all together. Something that's easier to show you with examples. This is an ogive that's looking at the percentage of children at different ages who have had some form of formal schooling. So like if you look at this graph, you can see there are no newborns that have been to school at all. But by the time you're at age 1, like 10% of kids have been to daycare or whatever. As you go older, you've had more kids that have been like to preschool. And by the time you get up to like age 6, almost everyone has been to kindergarten or first grade or actual school. This only goes up as we go from left to right. That's because once you've been to school, you've been to school. And you're not going to go off that graph. It's just going to add to what was there before. So the percentage always grows because you always add on to what was already there. And when you get to the top, typically the line will level out because you're getting close to 100%. This is another ogive that's showing you the percentage of public buildings that were compliant with the Americans with Disabilities Act. You might or might not know that the Americans with Disabilities Act was actually written by a guy from Iowa, Senator Tom Harkin, and it passed back in 1989, and at that point you can actually see on this graph less than 10% of public buildings were actually compliant. That's because if you think about old public buildings, they have stairs everywhere. In the next 10 years or so, more and more buildings became compliant. That would be like when we put in a ramp down by the cafeteria at Garrigan. And over the years, it's gone up and up and up. I actually looked recently, and today it's about 93% of buildings that are compliant. It's never probably going to be 100, both because if you don't make a renovation, you don't have to make a building compliant with ADA, and also because some buildings can be exempted for historical reasons. It's not like they're going to put an elevator right in the middle of Independence Hall. But as time goes up, you have more and more buildings that fit that characteristic. Again, typically it's going to level off at the top as you approach 100%. A couple of other examples of things that would be stuff you might use an ogive for. I have the percentage of babies who have spoken their first word at different ages. Some people speak not long after they're born. Some of them can wait until they're even about 2 years old before speaking, but once a kid's spoken, they never shut up. Or you could think about like when new ads are introduced in the Super Bowl, some people see them during the game itself. Some people might see it the next day when it's like on the news and everybody's talking about the cool ads. Sooner or later, some of those ads go into regular rotation of advertising, and more people will see them over time. A couple of things you always want to do when you make a graph. You want to make sure that you do include a title and an explanation of what the graph's about, and that you choose the right kind of graph for what you're doing. That if it's like counting up things, that's probably a bar graph. If it's percentages, it's probably a circle graph. And if you're looking at how things change over time, you probably want to use a line graph. Now, one of the things you'll do when you do your project is you will be asked to make a graph. And you do want to make sure that you do things right when you do that. You should always include a scale or a legend so you say how big the numbers are rather than making people guess. And it should always go up by even intervals. Bar and line graphs always should start at 0 or at the very least include where 0 is. If you don't start at 0, you are always being deceptive. You want to make sure that you compare things that are of comparable size. You don't want to suddenly have one group that seems bigger just because it's naturally larger. Percentages on a circle graph should add up to 100. You don't want things to overlap, and you got to make sure you account for everything. If you make a pictograph, you want the pictures to be the same size. And you always want to avoid 3D graphics. I'll show you some examples of how that goes wrong here in a minute. This is something that today is much more of a problem than it used to be because 3D graphics are really easy to do in programs like Excel, and they look really cool, but they can also lie really easily. Basically, you want your graph to show the truth. You want to show the information you're trying to convey and not all kinds of other stuff. And so I want to show you some examples of some bad graphs, because when you get to your test, you're going to have to look at some bad graphs and tell me what's wrong with them. Here's an example of using the wrong kind of graph. We're trying to compare how well a kid did on different tests like words and spelling and silent reading. And they made a line graph to do that, but they probably should have compared it with bar graphs because we're not looking at changes over time, we're just comparing raw scores. Here's an example of a bar graph that doesn't start at 0. It actually came from the website of a high school in Nebraska, and it makes it seem like their ACT scores are way higher than average, when in fact they're just a couple points higher than average. And so, by starting at 20, it's making the small difference seem like a big difference. Here's one that's from an ad for KFC, and it makes it seem like their product is way healthier than Taco Bell and Wendy's and Burger King. But when you look at the bottom, you can see that the graph starts at 590 calories and it goes up to 720. And, yeah, they're a little bit healthier, but not really all that much. Another graph that doesn't start at 0 that you see all the time is the stock market graph that you'll see on TV or in the paper, which makes it look like the market is very volatile, like it's swinging widely all over the place. And in fact, those changes are rarely as big as they seem. Now, occasionally they can be, like right at the start of the COVID epidemic, the market truly did tank rapidly. But most of the time, even what looks like a big change on this graph, if you started at 0, that 0 would not only be down on the floor, it would wrap around and be a long ways in front of you. Here's two different bar graphs that show the exact same information. These are both looking at changes in housing costs in London, which is why it's in pounds. And you can see the one on the left makes it look like there's a huge increase, but the one on the right, which is the much more honest graph, makes it look like they're about the same and it went up just a little. Another thing I told you was important was to make sure you have even intervals that you go by. This was something that was literally presented to the teachers at Garrigan, showing the results of our Iowa assessments. And if you look really carefully at it, you'll notice that we have a really big area that goes from 1 to 25, a tiny area from 25 to 50, a tiny area from 50 to 75, and then a really big area that goes from 75 to 99. And what this does is it makes things look like they're spread out differently than they actually are. Most of Garrigan's scores were well above average. Actually, they were all well above average, but it looks like they're not nearly as high as they are because they put such a big gap between 75 and 99, and this is not divided evenly. One of the worst graphs I ever saw appeared in the Algona paper a few years ago. I assume this graph was intended to show what percent of the United Way goal they'd taken in for money. But it wasn't labeled to begin with, and there are all kinds of other things that are wrong about it. It doesn't start at 0, and if you start looking at the side, it goes 5,000, 5,500, 6,000, 6,500. It looks like it's counting by 500s. But then once you get to 10,000, the next number up from there is 15,000, 20,000, 25,000. Yeah, usually the point of these thermometers is to show how close you are to making the goal. I have no clue if we're close or not. If the goal's 40,000, the graph makes it look like we're maybe 2/3 of the way there, but we're really way less than half. So yeah, there's nothing about this graph that's really very good. Here's a sort of pictograph the little kid might actually draw. Maybe they ask different people, what's your favorite animal? And the problem with this one is that the same number of people said horse and other, which we got pictures of fish for, but it makes it look like there's more horses than there are anything else. That's because they drew horses really big because horses are big animals, but they drew fish and cats really small. And these should be the same size. Here's the same information presented the way it should be on a pictograph, where we have the same size pictures for everything, and it's much clearer to be able to see that cats were actually the most common answer. I said earlier that something you always want to avoid is 3D graphics. That's because 3D graphics make big things seem bigger than they are, and they can make small things seem bigger than they are. Here are two different pie charts that are again showing the exact same information, but on the left, the green sliver looks a lot bigger than it does on the right because it's three-dimensional and it's popping out of the graph. The blue one, on the other hand, part A on the left, looks smaller than it actually is because it's in back, it's like hidden behind, so it's harder to see. Here's another one that are showing the same information, and again, on the top one, the 3D graphic, you not only are seeing 55% of the circle, but you're also seeing the whole front, and that makes this look like even more than what it already is. And when you show things that go into perspective, you can make differences seem even more than that. On the bottom left, there's two graphs that again are showing the same information. It's hard to tell on the 3D one that the first and third bars are actually the exact same height. The first one looks like it should be way bigger than the others. So again, when in doubt, avoid 3D graphics. One other thing to avoid is overlapping categories. This is a graph I came across where they're looking at the percentage of people with AIDS that fit in different categories, and you can see gay men, blacks, women, heterosexuals, and teens. The problem with this graph is there are people that could be in as many as 4 of those categories at once. You could have a teenage heterosexual black girl, and she fits lots of those categories. My bet is whoever made up this graph was trying to show that the most likely people to get AIDS are gay men. But I don't know that. If that's what you're looking at, then maybe do one where it's comparing gay people and straight people. Here, when you have overlapping categories, you can't really make good comparisons. There's one other key thing I want you to remind you of, which was that you want to make sure that your categories always have the same size. This is a problem that you'll often see when people make comparisons among, for example, US states. I don't care what characteristic you're talking about, there's going to be more of it in California than there is anywhere else in the country. I actually heard some politicians recently talking about how much crime there is in California. And I've heard people talk about crime in places like New York as well. Well, the number of crimes that you have in a place like California or New York isn't really what matters. What matters is how does that compare compared to how big those places are. When you've got 40 million people in a place like California, there's going to be more of absolutely everything. And there's going to be a lot less of it in places like Iowa. But what you really care about is the rate of crime or the rate of a lot of other things compared to the population. And so you do want to make sure that you have those out. Now, again, what's going to happen when you end up looking at your worksheets and tests is you're going to see some examples of bad graphs, and I'm going to ask you to come up with some things that are wrong about them. And that's most of what we want to do with Chapter 2.